work on those, but it's probably best to spend an hour every now and again just working on those machines so that you become familiar with how it differs from what you set up at home. Okay? Did anybody try installing it on Apple with Apple Silicon? Very good. So you've all read the warnings. Excellent. Okay, so we're ready to start. As I say, I'll break at about 1:15. That's when Adam Walker from Optiva will join us. And we'll see what he has to say at that time. Let me just check if that's working. That's okay. I'm hoping that it will work okay as we get going. Right. So, one of the things I mentioned on Tuesday was that we try to minimize the size of digital logic circuits to minimize the cost of implementing those circuits and to enhance their performance because smaller circuits are faster, and also to enhance reliability because designs with less components are more have higher reliability. Obviously, there's some dependence on how many components are connected together. So today we're going to formalize those statements a little bit. It's going to show how that's done. But in order to understand how it's done, you need to understand that there's a mathematical theory underlying all of this, which is called Boolean algebra. You can read about it in Wikipedia if you don't have a text or something like that. I'm going to just quickly cover the main theorems and axioms of Boolean algebra. You don't need to remember them all or anything like that because, as you know, in theory exams, you're going to have an open book anyway. And I really don't see it as being that important. There's only one or two rules at any one time that you make use of. And they're the ones that you'll see today are used in simplifying circuits. So the first one of these these axioms of Boolean algebra is that if you OR some variable, Boolean variable x with 0, then you obtain x as the result. Because obviously it's not boring, it's something with 0 doesn't change the value of it. If you OR 0 with 0, it's still 0. If you OR 0 with 1, it becomes, it's 1, right? There's a so-called dual, and I'll formalize the notion of what that means shortly. A dual statement in which if you add a Boolean variable with 1, that doesn't change that variable's value either. So x and 1 is x. Try it again. 0 and 1 is 0, 1 and 1 is 1. So you're still left with x. And x, of course, is just a Boolean variable, has two values, either 0 or 1, which is true or false, effectively. Okay? So the next axiom is that if you OR x with 1, then you're going to get 1. Similarly, the dual is that if you AND x with 0, you're going to get 0. All right? That should be pretty evident to you just from the truth takers. I'll go through these reasonably quickly. There's 2 pages of them. The next one is known and has a very strange name. You can see, I'm not even sure if that's really the right way to pronounce it. But it says that if you take some variable and OR it with itself, you just get itself back, right? Similarly, if you add a variable with itself, you just get the value of that variable back. If you complement not x, which is what that says, then you get x, right? So if you've got not x and you complement it, you let fall the not of not x, then you get x. That seems pretty straightforward. That doesn't have a dual. This complementarity is useful. If you OR x with its complement, then you get 1 because either x or not x is true, right? Has to be. And if you add x with its complement, you get 0 because there's always either x or not x is going to be 0 because of the 2D relationship up there. The result's going to be 0. The Boolean variables are commutative, expressions are commutative, and they're also associative. Okay? We'll let the fiddle around there. You have to, there's up to, it's just a matter of shifting in frequency. Yeah. So, it's that. Right. This is sort of more lengthy. These are all effectively theories. You use the axioms to prove them, as we'll see in a moment. The first one is a little bit weird. On the left is an expression that you might see as being trained through normal algebra. But on the right, the dual expression is a bit unusual because here you can see that or and are effectively similar value. So if you OR x with y and z, you're going to have x or y and x or z. And it's pretty easy to show that, or at least to that verify that that's correct. Look for this one. We have that if you have x or y and z, I think that's the one that we're doing, isn't it? This is equal to, or the claim is that this is equal to x or y and x or z. And this is pretty easy to show because if you the equivalence is easy to show because if you multiply these things out or form the logic on them, x and x is x, right? Or x and z, we have to write it out. Or x and y, we have to write that one out. And you have y or z. Y and z, sorry, like that. So this is x. We're just using a dependency for that. And then x or x and z. Can anybody tell me what that is? This is literally just x. Well, we could write a 1 there. And 1 or z is just 1. So really this simplifies to x. This
1, 2.
Right. Similarly, this covenant, x and x and y, that simplifies to x. Well, 2x's, x or x is just x. And finally, we're left with y and z. Y and z. So that's equal to the left-hand side.
The black pen.
I do have a black pen too. I will use it. Sorry, I used the red one. They're the only two colors I have though. How are we going with? Right. So moving down from the top there, we've only got a few minutes to go. The writing theorem is really probably the most important one that you need to know. This is the one that we'll make use of in subsequent work to simplify Boolean expressions. Okay. So I'll just take a break there and flick over to Zoom so that we can catch Adam when he comes in. Are there any questions yet on what I've talked about here? Okay. So let's just out of that. Zoom in. Do that. It'll come up, no doubt. He may not be able to hear us particularly easily because we're only using a microphone on my laptop. And if that, yeah, I don't know how that's going to help him. It's the one thing. It's absolutely. So, well, how would you use the? Oh, it's such a choose that audio. No, that's turning it out. Yep. The settings. Because of an actual choice, you can combine that. Oh, yeah. But, thanks to the skill out. And it's to when it's going to work. You talk, that you got that, and you want to it. To want to be less. But so it's give that. He doesn't get spit that. Not actually using Teams, but I thought he told. Don't worry, I think he'll be doing the most of the talking anyway. Oh, I see. That's for the speaker, is it? Yes, for the speaker. And with FST, I think that's just what we're looking for. It's not that anything. No. And you'll like to be like, yeah, it looks within the room, it's fine. And if you're staying in Portland, will pick up that night. That should be fine. You get in, like, you want to get some cards that you will get your attack. Yes, please. I think it would be good to have the big and cover. Hey, Adam, can you hear me? Hey, yes. All right. I can. The rest of the class probably can't. Let me just see whether we can get you onto better speakers for them.
All good.
Yeah, I think we can hear you now. Do you mind saying something?
Yep. Hello, everybody.
Yeah. Yep. I think they can all hear that. So,
they get all that.
Your screen, are you able to do that, or do I need to allow that?
I was just gonna speak. I don't actually have any slides.
Great. All right. I'll get out of you. Right.
It's all good. It's all good.
Let me just see if I can maximize your I think you can hit it. Sorry? You can hit it. Hit it, you reckon? That worked. All right. See, everybody, the use of today, they're much better at tech than I am.
All right. Well, thanks for having me, here, Oliver. So yeah, I'm Adam. I'm one of the FPGA team leads here at Optiva Sydney. So as you probably know, we're a sponsor of this course, and I'm here to let you know a little bit about myself, about Optiva, and how we use FPGAs. Later in the course, I'll also give a much more in-depth talk about what the FPGAs are really doing here. And we're also looking at hosting like a lab type of thing here at Optiva Sydney, where you can come and effectively build a somewhat simplified but real trading system with the dev board. So I originally got interested in FPGA engineering while doing a course a lot like this one in my undergrad at Auckland University. And after graduating from a PhD at UNSW that didn't involve FPGAs at all, I decided that I wanted to get back into them. But FPGA engineering was pretty niche at the time. It was the early days of FPGA-based trading at least in Asia Pacific. But I managed to get a grad role here at Optiva. But since then, I've had a couple of other FPGA engineering roles in Sydney. One in a FPGA-based network card startup, and another at another trading firm in Sydney. But a couple of years ago, I returned to Optiva as a team lead. So if you don't know, Optiva is one of the larger global low latency trading companies. We trade in pretty much every financial market in the world, and a good chunk of what we do is latency sensitive. So that means that trading opportunity will exist for microseconds or nanoseconds, and if you are too slow, you don't get it. So as such, we end up being quite a technology-driven firm, where the technology is aimed at just making these trading decisions, sending these orders, as fast as possible. So obviously that's where FPGAs come in. And again, that's something I'll talk a lot more about, like in a later lecture. But at a high level, data comes to us from the market over Ethernet as packets, and if we see an opportunity, we will react, send an order to the exchange, again using Ethernet packets. Now, if you were to do this with a software stack, packet would come in over Ethernet. The network card would package it up, send it over PCI Express. It would make its way into the CPU cache. CPUs I kind of do one thing at a time, so that will get around to having a look at that packet at some point, make a trading decision, and then if it decides to trade, it will do that in reverse. Package it up, send it over PCI, and the network card will send it out on the network. Now, all of this is going to take a long time on, electronics timeframes, so like nanoseconds. So what we do is we just skip most of that. Ethernet market data in the form of packets comes straight to the FPGA, straight to the digital logic, and we make a trading decision and send it back out. And at a high level, yes, here we go, a diagram, very good. So at a high level, the system is very simple. And that's basically what we do all day. So it's an interesting kind of mix of like low latency or highly optimized I/O. So you better get those Ethernet packets on and off the FPGA as quickly as you possibly can. And also mapping those trading algorithms efficiently to the FPGA fabric. And the latter is more than just pure digital design, right? So it's also about understanding networking, data structures, and algorithms. We can't just import, hash map like you might do in software. We have to implement our own, and we probably have to tailor it to the, the trading problem at hand. We also do a lot of, hardware software co-design. Obviously, this kind of reactor logic, the hot path, you've got to put it in the FPGA. Otherwise, it won't be fast. But putting the whole of Optimus pricing stack is obviously not even going to fit. And if it did, it would be way too slow. So a big part of our job is finding this kind of optimal partitioning point between hardware and software. And I guess, to sort of start finishing things off a bit, I just want to mention what I like so much about the industry. It's kind of one big competition. Whoever builds the fastest, and most capable trading systems will win. And that means that you kind of get to put your knowledge of digital design that you get in courses like this, along with algorithms, data structures, and networking to the test. And the only real limit is what you can build. And from the beginning of your career, at Optiva, you're really doing cutting edge work from day one. And if you come as a graduate and you have ideas that will genuinely improve our trading systems, then go for it. Right? That's how it works. And I think that's kind of great. Yes, that's really kind of all I had to say for an introduction. Thanks, Oliver, for having me here. And as I said, I'll be back later in the course to share a bit more nitty-gritty detail about what goes on the FPGA, and we'll also keep you posted about this hands-on lab that I mentioned. Thanks. Are we doing questions?
Well, we have 5 minutes about questions. If anybody has a question for Adam. They keep stunned them, Adam.
And I've stunned them, awesome.
who might be interested in joining in on this lab experience at Optiva? Yeah, that's what I thought. It would be maybe half the class or so.
Oh, that sounds great. Yeah.
Years at least. I don't know about the others. How many, like, drop your hand if you're a computer engineer. If you're still interested, put your hand up. Okay, so there are a few there's a few software engineers and comp sci students maybe as well that would be interested. Yeah, so we look forward to hearing more about that opportunity. And yeah, we'd love to have you talk a little bit more about the nitty-gritty detail later on in the year, if that's possible, in about 9 weeks' time.
Sounds great to me. Yeah.
Thanks, Adam. Thanks so much. All right. I'm sorry for the couple to Zoom.
Oh, no, that was fine. I got there in the end. All right. See you, everybody.
Bye now. Right. Right. Well, that brings us back to the everyday, ordinary stuff that we were talking about here. All right. You're all clear so far in what we've been talking about? Okay. Very good. So make a bit more progress on this. I'm actually hoping to finish this lecture today and maybe making a start on the next lecture. So I was at Theorem 9, Uniting Theorem, where the left-hand version is probably the one that's going to be the most comfortable familiarity to you as we proceed. But the dual version is very important if you're dealing with an alternative representation of logic, which we'll talk about today as well. At Law 10, we have the so-called absorption law, which is essentially summarized here. I used that a couple of times to get rid of Z here and then Y, etc. So that's about commonly used. And then there's two that are less common, that if you can observe an instance of them, and I know somebody has because there was a comment in the forum about it, if you can observe an instance of them, then it allows you to eliminate a term or a factor in your expression, and that's very useful. So I'll go to the consensus theorem because that one is perhaps a little bit more easy to observe. If you ever observe X and Y and not X and Z, note that X is here and with Y and not X is and with Z. And you also have an all with Y and Z, then you can eliminate that Y and Z term. Okay. It's not too hard to show that. That is one of the questions in the exercises that I think I've provided answers for already on the web for next week, and we can talk about it next week during the hour that I'll allocate to sort of free-ranging Q&A. All right, I'm not going to go into the details anymore at this stage, so I'm happy to take questions at the end if there is some specific question about things. Now, very importantly, up the top here, we have De Morgan's law. We frequently do make use of De Morgan's law, which essentially says that if you've got a bunch of terms brought together, you take the complement of them, then that's equivalent to ANDing the complement of each one of those terms together. And there's a dual version on the right there. And then there's a generalized interpretation of that statement. If I have some function f, which involves n variables there, as you see, x1 through xn, zeros, ones, ors, and ands, then if you complement that function, which is given by the red f at the top, what you end up with is the same shape of function, but each one of the variables has been changed, has been complemented, And instead of zeros, we use ones, and wherever there was a one in the original function, it becomes a zero. Wherever there was an or, it becomes an and. Wherever there was an and, it becomes an or. So it's quite a powerful observation, quite a powerful law that establishes a relationship effectively between and or, and the ability to complement functions. So here's a nice example of this in play. Given that we have function f, which is expressed as x2 or x1 and x3 bar, or not x3, then the complement of that function is the same as just putting a bar over the entire function. Of course, that's an or of two terms here. So that can be split up according to this representation up here as the and of two complemented terms. And the right-hand one of these is an instance of what we see on the right here, the complement of two variables that are AND together. So that can be expressed as the right-hand side over here, whereby we observe that x3 now gets double complementation, so it just becomes x3 ultimately. What you end up with is a similar shape to the function. X2 has become x2 bar, the or has become an and, x1 has become x1 bar, the and has become an or, and x3 bar has become x3. So as promised, here was complemented now, and the ors and ands have switched roles. Okay? Is there any question on this? Okay, good. That's quite a powerful law, which we will make use of quite a lot. It's not hard to remember it, though. It's pretty easy. Okay. We did illustrate the dual versions of expressions. So the dual can be derived by replacing ands by ors, zeros by ones and ones by zeros, just as with De Morgan. But we leave the variables unchanged. So this is the expression of duality that we have, rather than complementing all of the variables. When you take a complemented function, all it's saying is that if we have some function of n variables, zeros, ones, ors, and ands, then we can also form the dual of that by using the same variables, swapping the one for zeros, ones, ors for ands, and ands for ors. Okay, so this allows us to generate more theorems that we're not actually rewriting the expression as we could be doing with De Morgan. All right. Now, you can prove these theorems in various ways. I'm just going to show you quickly how to prove one particular theorem, the absorption theorem, which is the one that I used over here. And I'll prove it deductively, exhaustively, and using set theory. Okay, so you can use the axioms and theorems of Boolean logic to simplify expressions. So here we've added a one, or ANDed the first variable x with one, which we're allowed to do by identity, as we've seen. And then we use distributivity by taking the x out of both of these terms. So we're left with 1 or y, and 1 or y is 1, because that's just the identity expression again. And then there's the one that we're left with here is just reduced to x by the identity theorem. Okay, so thereby we've shown that this left-hand side is equal to the right-hand side. Now we can do it exhaustively as well. This can be hard to do, particularly if you're not strong at maths. You won't necessarily know which law to apply when and in what order. Some people are very good at it. Others, the average person like me isn't very good at that. So I can imagine that this is not particularly easy. You'll probably find it a lot easier to do this exhaustively using a truth table. So here I've listed the possible combinations of x and y. forms the product x and y, and then clearly the expression x or and x and y is just the two y's at the bottom, which just happens to be equal to x. So we've exhaustively shown that for all possibilities, the left-hand side is equal to the right-hand side. A more interesting way of thinking about life is to think with in terms of sets, where the rectangular box represents the universe. We can form a variable within that, as in this circle, this set x, for all of the contents of that set x. We form a conjunction or and by the intersection of sets, and we form the disjunction or the logical or by forming the union of sets. So in this particular case, we need to evaluate x or x and y. So we want to form the union of x on its own with x and y, which is just this intersection in the middle here. But of course, the union of those two is just x. So clearly they're equivalent. All right? Okay. I don't think there's anything particularly novel about that. So, it's important to note that in the absence of parentheses, so we're not talking about the HDL here, we're talking about Boolean expressions. There's a precedence between these operators, not is higher than and, which is higher than or. So that allows us to unambiguously interpret an expression like that as on the right-hand side here, where the and has to be performed before we bore it with the second term. As far as the second term is concerned, we've got to form the complement of these variables before we add them together, and then we OR them together with x1 and x2. Okay? We don't often use the dot. I should just mention that everything we've just talked about, the axioms and theorems of Boolean logic, in many texts, that might take up a chapter on its own, and one could do that. But I think in this course, we're really interested in designing circuits, and so all we need to know is that these theorems and laws exist. It would be nice if you became fluent and proficient at using them, but it's not essential what we do, as you'll see. Okay, so let's get back to how do we derive what a circuit should be given some truth table or a function. So let's say we're given this truth table up here, and we have to draw a circuit for it. Okay, so what the circuit needs to do is output a 1 whenever x1 and x2 are both 0. Similarly, it needs to output a 1 whenever x1 is 0 and x2 is 1. And it needs to output a 1 when x1 and x2 are both 1. Right? So we can express that as I've done here in this first row, by simply combining all the valuations of the function where the function has to be 1. So this is not x1 and not x2, or not x1 and x2, or x1 and x2. Okay, so they're the function valuations, or the valuations of the inputs that drive the function to 1. And once we have this expression here, it's easy to see that as a circuit, or realize this is a circuit. So the hard part is really just transcribing the truth table into this expression. So we see here, this lower AND gate is actually taking the complement, not x1 and not x2 as its inputs. So that's realizing the first term. The one in the middle here, it's realizing not x1 and x2, right? Because it doesn't have a complemented version of x2 going into it. And the AND gate at the top is realizing x1 and x2. And finally, the OR gate is just ORing all of its terms together, those AND gate outputs together. Right? However, given that we now know that we can simplify things, we might observe that there's a few opportunities within this expression to combine variables together, and they might derive a simpler expression. In this particular case, you might observe that the non-x1 is common to the first two terms, then x2 appears as both in both complemented and uncomplemented form. And that means we can apply that uniting theorem that we saw. So I'm going to do things a little bit more elaborately so that you see each of the steps that it could take in simplifying this expression. In the first step, all we're doing is replicating this central term, not x1 and x2, so that we can combine the left two terms together and then use the second copy and simultaneously combine the right two terms because they're common in x2 and have x1 appearing complemented and uncomplemented forms. So I do them separately here on the left-hand side and here's the right-hand side of those two. So that's using just the dependency on this term here. And then we can apply distributivity on the first two terms and the second two terms, which is here. Within these, we see that we can apply complementarity to eliminate x2 far or x2. That just becomes 1. Same here. x1 bar x1 becomes 1, as we see here. And then we can use the identity to essentially simplify that to x1 bar x2. Now that expression already appears much simpler than this expression up here, and this is just going. You could just go in one step if you could see this using the uniting theorem. The resulting circuit looks like this, and clearly that's a simpler circuit than the one above, right? So that's why we wanted to know about Boolean algebra, so that we could systematically simplify expressions. Albeit we have to be able to recognize the opportunities for when to apply it, and we'll talk more about ways of guaranteeing that soon. I just want to make a few more observations now. I want to talk about the circuit cost. So as you saw here, clearly this is a smaller circuit. It's got less gates. It's got less inputs to some gates because this gate here has 3 inputs, whereas here it only has 2, etc. So in practice, logic gates are made of transistors, and it's the number of transistors that are used that correlate with silicon area that's used to implement that circuit if you're putting it into a chip. So circuits with fewer gates and gates with fewer wires require fewer transistors. Okay? And that immediately leads to less chip area. And so we're only going to talk about circuits in terms of logic gates. We will, right at the very end, have a look at how logic gates are implemented, but it's really almost, from my perspective, it's just additional knowledge. I'm not expecting you to make use of that during the course. I'm hoping that you won't feel like you're missing out. If you do, then maybe you want to read ahead. So unless stated otherwise, we're going to use as a metric for the circuit cost the number of gates plus the number of inputs that are needed to implement that circuit. Okay. So by that measure, the first circuit that we drew on the previous slide has a cost of 17, and the second one has a cost of 5. Let me just show you how that is. Whoop, that went the wrong way. Didn't it? No, of course, that's all going to work now. Here we go. Right. This one, how many gates are there? The top one. 1, 2, 3, 4, 5, 6. Got 6 gates. How many inputs? 1, 2, 4, 6, 8, 11. So 6 gates plus 11 inputs costs us 17. What about this lower one down here? 2 gates, and we have 3 inputs, so it's got a cost of 5. Okay? It's a rough guess at cost. It's not precise. Any questions? Yeah? Yes, good question. We'll get to it. All right. So I just want to summarize, and then we'll come to it. Okay, so this is what we did to synthesize a logic circuit. We included a product term for each row in the truth table with the function value of 1, right? That's what we did. And then we summed or ORed them all together, all those product terms. And then we simplified the resulting expression using Boolean algebra, and finally, we drew the circuit. Okay? Now, I want to focus on that first term, which is answering your question. All right? How do we derive those AND terms for each row in the truth table with the function value of 1? Well, you need a little bit more theory for that. We need to introduce this notion of mean terms. Okay? Now, a midterm is a product term in which each of the n variables that you have in a function appear exactly once, and they're either complemented or uncomplemented in that min term, right? So here we have a truth table with 3 variables in it, x1, x2, x3, and that means we'll have 8 rows, and therefore there's 8 combinations of those variables that can appear. And over on the right-hand side is listed the second min terms. So 1 for each row in the truth table. So a min term is formed by combining the variables in a certain way. So if the variable its complement is 0, then the value of the variable is 0, then it appears in complemented form in the min term. And if it's 1, in the valuation of the variable is 1, it appears in uncomplemented form in that min term. Okay. And so we see that the min terms, if we list them in the same order as a systematic elaboration of the valuations of the variables that make up that function, they're going to be numbered according to which variables appear in uncomplemented form. So here we have 0, now they appear in uncomplemented form. 1, we have only x3 appearing in uncomplemented form, and so on all the way through to M7, being all 3 variables being uncomplemented. Okay? So, that's effectively this point here that I just made. What is important to note is that the ith min term is 1, has the value of 1 in the ith row, and is 0 for all other rows. Take an arbitrary one, let's say F3, for example. All right? If we have the valuation of x1, x2, x3 being 0, 1, 1, then not x1 is going to be 1, x2 is going to be 1, and x3 is going to be 1, and therefore the product is going to be 1. But take any other valuation, 1, 0, 1, for example, and you'll see that non-x1 is now going to be 0 because x1's valuation is 1, and therefore the product term is going to be 0. So the min term is only 1 in its corresponding row, and it's going to be 0 in all other rows, taking the valuation for those variables. All right? M0 is going to be 1 in row 0, because in that row, every one of these variables has a valuation of 0, and therefore its complement is going to be 1, and therefore M0 is going to be 1. But in any other row, at least one of those variables is 1, and therefore its complement is going to be 0, and therefore M0 has to be 0. Okay, I think I might have reached the limit of your understanding. Who's got it? Who's not got it? Right. What would you like me to explain more? What's causing lack of why are you not understanding what I'm saying about M0, for example, just picking on one min term here, and its value in each one of these rows. In the first row of the truth table, when x1, x2, and x3 are all 0, the complement of x1 and the complement of x2 and the complement of x3 will have complement of x1 being, since x1 is 0, it'll be 1. Complement of x2 will be 1. Complement of x3 will be 1. And if I add those 3 ones together, the result will be a 1. Yeah? However, on any other row, at least one of those variables is 1. And if I complement that variable in this min term, it's going to be 0. And therefore, that product is going to be 0 overall. So that product, not x1 and not x2 and not x3, is only going to be 1 in the very first row of this truth table and 0 in every other row. And is there any other doubt about this? Not to make the product each. Say again? We need to make the product each row to be 1. Well, the min-terms are 1 in their row and 0 in every other row. So M6, I'll take M7 as an example. It's easier for me to reach that one. It's only 1. M7 can only be 1 in row 7 of the truth table, because only that row has the valuation x1 equal to 1, x2 equal to 1, and x3 equal to 1. So only in the 7th row is M7 going to be 1. M7 in row 6 would be 0, because x3 is 0. And if I add 0 with 1 for x1 and x2, I'm going to get 0 as a result. So depending upon which row this min-term appears in the truth table, is to have a different value. Perhaps I should move on to see how that's used, this concept. So a function can be represented by an expression that's written as a sum of min-terms, and that's effectively what we did when we looked at how to draw the circuit for that given expression. In order to achieve that, you would add every min-term together with its corresponding, the value of the corresponding function. So let's go back to the example that we had. We looked at this truth table here. The function values are 1, 1, 0, 1. Over here, I represent that it's min-term 0 and 1, min-term 1 and 1, min-term 2 and 0, min-term 3 and 1. So that effectively cancels out min-term 2 because it now has a 0 in that term, right? In that product. Therefore, I'm left with min-term 0, 1, and 3. And this was the original expression that I put up before. Does that answer your question? So I've derived it from understanding what the min-terms are and just adding every min-term with the functional value for that for that minterm corresponding to that row, right? So that gives me what minterms are represented within the function. I can write that in a simplified way as just the sum of minterms 0, 1, 3, or just sigma m lowercase m minterm 0, 1, 3 to indicate what minterms I need to represent that function, right? So if a logic expression just consists of a sum of product terms, as I've illustrated there, that's a so-called sum of products representation for a function. And if each one of these product terms is a minterm, as it is in this particular expression, they're all minterms. There's only two variables, and every term has both variables that are either complemented or uncomplemented, so they're all, by definition, minterms. Then that's called a canonical sum of products representation of the function, because there's only one way. The canonical means this is the one and only maximal way of representing that function using minterms. Okay? Every function only has one canonical sum of products representation. Okay, so this is just terminology at this stage. But it's important because if we're representing a function in shorthand, it's just a sum of minterms. It's important to know that that means this function does not contain minterm 2. That means it's 0 in that row of the truth table. This tells me where the ones are in the truth table. Okay? So every Boolean function has just one canonical sum of products representation. Okay. We're up to 41. Making decent progress. Let's have a 5-minute break and we'll review it. Are there any questions at all in the morning? Have a break. Feel free to have a break. Get in. Sorry to lose. Okay. Any questions? Yep.
Would you recommend sort of memorizing and implementing askable rules?
I don't think that there's any point in memorizing them. What I do think there is point in is going through them one at a time and understanding each one of them and at least arguing for yourself to your own way of thinking. Yes, that makes sense. You know, for example, there are a few good examples where that makes probably sense. So, for example, where's a good one? Well, actually, this the factoring one, the non-quality, that sort of is easy to argue, logically, because in order for the function to be true, both these terms have to be true, right? Yeah. But x can't be both true and true, or if x is true, that's Bayesian's bar, it's false. Therefore, what z would have to be true. Yeah. So if x is true, z has to be true as well. Yeah. Right. The other alternative is that x is false. Then this is true. It must be that y has to be true. And so therefore we have that second term. And either one or the other has to be true for the other to be true. Right? So it makes sense. But you less of go through and try and prove it, like we've just argued it, hand wavy sort of thing, that it should be true. But, I don't think that there's no merit in memorizing it.
Very nice. You could solve the exercises in the next hour or
no. Next week is when I'll start with the exercises. And I'm not going to solve them. I've given you the solutions.
No.
I'll be here to answer questions that you had, either about them or about the labs or about any of the content in the course.
Listen, the solution, it's not all the time exercise.
No, just start one.
What's some decision for next week? So begin.
Not if I won't be giving any more answers to those particular to that question set. You'll note the ones that I don't star, usually they have an answer in question set. So if you have a look at the question set, the answer's there. So if you figure out an answer, you'll be able to see whether you're right or wrong. Okay? And we might be able to go over one of those if you don't understand how I did the book. Yes.
I know in the first lecture you were talking about the extraordinary like fail,
Yeah.
right?
Yeah.
Like the data content that gets a lot harder. Well, like would you say like the reason why I measured the later content? But it's not understanding.
You're asking the wrong person because I don't understand. Really, I don't get it either. Why is it? Look, the one thing that does stand out is if you have trouble with the labs, you're going to have trouble with the track exam.
Yeah, it's
So if that's the way to stay on top of the labs is to do, like I said, to do them every week.
Yeah.
You get them done.
yeah.
And do them yourself as much as you can. And it's okay to ask for help, but you've got to come up with a solution that's your own. And if you've done that, I don't think you're going to have any trouble with the practice app bill. I should say, not everybody fails because they failed the practice exam hurdle. Out of the last year, there was one person that failed that hurdle. Sorry, didn't pass the hurdle, that failed the course overall. 21.
Yeah,
But it does occur.
so I had a very
So if you're doubting, I would prefer that you drop the course early so that you've got some alternatives. You allow some of those that are on the waivers to come in. If that's what you're asking.
yeah, I didn't. It's like because the content right now is fine, but like maybe it'll get a lot harder. Like the
I don't think it does. Like it's this course is track loaded with kids. It has to be.
Yeah.
You're not going to understand what you're doing. I have to figure out it.
yeah.
The rest is pretty practical. I'd say the first three lectures are probably around 3 or 4 lectures of the half.
Oh, okay. Yeah, thank you.
Sorry.
I have some fresh learning about historian drugs.
But okay, look, I can't talk about that right now because it'll take probably 5 minutes. And we're almost to be able to 5 minutes. What's more, the thing that we ask on the following is first thing you should be asking is the lab demonstrators if you're having trouble with parts of the lab or installing software, they can give you a hand. Also, one of the guys that's answering questions, and he's available to give you one-on-one support as well. So if you've got a specific question about it, I would suggest that it's going to be the best ones. But if you want to ask the question at the end of the lecture, I can have a quick look at what it is today, so I don't forget to get I think we might keep going.
It's not different from like adding the measure. The overall cost of it is like if you had
Yes. So that's why we want to use Boolean algebra to simplify it as much as possible. Yeah, that canonical form, they're expensive. Very expensive.
so like so sometimes then like it costs us suppose 90, like the canonical part, like the cost myself. So I reduce it to 9, but after that it's like impossible to like I can't think of any ways like shorten it.
Well, it might not be possible to simplify it. Not every function has a simplification.
Right.
Okay? The exclusive OR function is impossible to simplify. Okay, let's continue on before I have nobody to listen to. Right, where were we? We were on slide 41, weren't we? Right, we've done that. So, I think this might answer your question. All right, so let's say we have this 3-variable function, which is sum in terms 2, 3, 4, 6, and 7. Okay? You should be able to figure out in your mind. Min term 2 for a 3-variable function has not x1, and x2 and not x3, because that's binary 0, 1, 0, 2, where the zeros represent a complement and the ones represent not complement, right? So let's say we've got that function. The canonical SOP expression is, as I've just started explaining, starts with that midterm term where x2 is uncomplemented. It ends with that midterm 3, 4, 6, and 7. So that's the canonical sum of products expression. And if you wanted to figure out what the cost of that would be, there'd be an AND gate, another AND gate, another AND gate, another AND gate, another AND gate. That's fine, isn't it? We've got 1, 2, 3 inverters, so that's 8 gates. And then we have one big OR gate, right? So that's 9 gates. And we've got 3 inputs for the inverters. We've got 3 inputs to each of the AND gates. So that's 15 plus 3 is 18. And we've got 5 overall, which is 23, plus the 9 gates that we had. So 32 would be the cost of it. Pretty high, right? Okay. So we can simplify that expression using the uniting theorem here. I've combined the first 2 terms, for example, to eliminate x3 bar, x3 and x3 bar, right? Similarly, you can combine, what can we combine? The next 2 terms to eliminate x2, and finally the last 2 terms using dependency to replicate that 4th term to eliminate x3 from those expressions. That gives us this simplified form. That's in sum products form because it's a sum of product terms. But we can now see that actually we can simplify this further because we have x1, x2 and not x1, x2, so we can combine those 2 together to eliminate x1. So ultimately we're left with this expression here. This intermediate form, that is not sum products because we've got added a sum term here with x2, so it's not really in sum products form there. But the last version is a sum products here. Okay. This last one, what's the cost of this? Well, we have 1 inverter, 1 AND gate, and an OR gate, so 3 gates. 1, 2 inputs, that's 3, plus 2 inputs, that's 5. So was it 5 plus 3 is 8, 4. Much cheaper than the 32 we had before. Okay? Good. Right. So we've talked about min terms. Duality implies there ought to be a way of representing the function by focusing on the zeros rather than the ones, right? And that introduces the notion of max terms. So the complement of a min term is called a max term. So going back to our table, 3 variable truth table, min term 0 at the top has not x1 and not x2 and not x3. We've already talked about in detail. That's going to be 1 in row 0, it'll be 0 in all other rows. Its complement is the max term 0 that we see on the right there, namely x1 or x2 or x3. How did we form that guy? Well, we used De Morgan, as is illustrated at the top there, to get this guy. Now, if the min term's 1 in row 0 and 0 in all other rows, what's the max term going to be? It's 1. It's going to be 0 in that first row and 1 in all other rows, right? Because in the first row, none of x1, x2, or x3 are 1. Therefore, it must be 0. But in every other row, at least one of those variables is 1, and therefore max term 0 would be 1. Right? Okay, very good. So all of the max terms are just formed by complementing the corresponding min term, and each max term is only a 0 in the ith. So max term I is 0 in the ith row and 1 in all others. So if we add these max terms together, we're going to get all of the zeros that are in function effectively. So let's see how that happens. So this is a bit of a tortuous statement. It's better to explain this by example. We've looked at this function already. We've seen it in previous slides. Let's say we have this function of 3 variables. That's the sum of the terms 2, 3, 4, 6, and 7. If we complement this f, then that's going to be expressed as all of the min terms that weren't present in the function expression, right? Because they're all the zeros, right? So if a function has 2, 3, 4, 6, and 7, then its complement must have 0, 1, and 5 each, but 0, 1, and 5 each, right? Because they're going to be 1 in the complement and 0 everywhere else. Okay? Now, what if we complement that again using De Morgan? So then by De Morgan, complement them, means them 0, 1, and 5 being worked together, is this expression here, which we can use De Morgan on in order to obtain the and of 3 products, right? 3 factors, if you like, where each factor is the complement of the corresponding mean term that we had. And of course, we can use De Morgan again to expand those. So what it would look like, actually, when we've finished all that negation, is this expression here, namely max term 0, the complement of mean term 0, max term 5, max 1, sorry, max term has got base 3 big complement, and max term 5. So this is what the function would look like. So the function can be represented as a sum of min terms 2, 3, 4, 6, 7, or as the product of max terms 0, 1, 5, the numbers that are missing from that list that you use to form the min terms. So on the left here, we have this observation that a function's complement is just the missing min terms from the functional expression. And on the right here, we have this equivalence between a function in terms of its sum of min terms, this product max term representation. In both cases, we're using the missing numbers from the list in order to derive them. But is that clear? Are there any questions? Yeah?
Will the cost be fine for SOP and PO?
No. You should be able to figure that out. We've talked about the cost of sum of min terms being 32. We did that before. What's the cost of this one? Well, we've got 3 OR gates, right? We've still got 1, 2. Oh, we've only got 2 inverters here, right? X3 and X1. And we have 1 AND gate overall. So 2 inverters, 1 AND gate, and 3 OR gates. So 6 gates altogether. And we have 2 inputs to the inverters. We have 3 inputs to each of the OR gates. So it's 9 plus 2 is 11. And we have 3 to the OR gate, to the AND gate, sorry, the final AND gate, which is 14 altogether, isn't it? 11 plus 3. 14 plus, how many gates was it? 6. 10 plus 6, so 20. Much cheaper than the sum products, right? The canonical sum products. Okay, so when the logic expression consists of sum terms like these, right, that are factors of a logical product and it's said to be in a so-called product of sums form as opposed to sum of products form. They're sort of complements of each other, these 2 expressions, but it's clear this is a product of sums, right? And if each of the sum terms is a max term, that is a canonical product of sums form. whereby, again, there's only one canonical representation for every function. Okay. Can't remember what's on the rest of this slide, but we're still using exactly the same function there. We now know that it can be represented as a product of max terms. I think we're just reinforcing that fact that there's this equivalence between sum of intervals and product of max terms. We start off with this expression. We can then use Boolean algebra again to simplify this expression, because we know in those first two terms, x3 appears in complemented and uncomplemented, also can use the uniting theorem there. And similarly, between these two terms, x1 appears in complemented and uncomplemented form and can therefore be eliminated. So we can end up with this simplified expression at the bottom here, right? Which again is going to be quite a bit cheaper than the 20 that we've previously calculated. What is the cost of that? One inverter, but 2 OR gates and 1 AND gate, so 4 gates. 1 input, 3 inputs, 5 inputs, 7 inputs, plus 4, cost of 11, right? Compared to 20 that we had. And if you use the distributed property on this, because you've got x2 at both, you end up with this expression. What's that? Product of sums or some products for? SOP. You all see that? Okay, good. I think we derived the cost of that before. Can't remember what it was. Was it 8 or was it 11? 8. I think 3 gates and 1, 2, 3 gates, yes, and 1, 2, 3, 4, 5 inputs. Okay, so this is the last slide with work on it. The question is for you now to try it out. Derive the canonical sum of product and product of sum expressions for the 3-valued function below, and minimize each expression using Boolean algebra, and sketch the resulting circuits and compare the possible designs. Okay? You want to try and give that a go, and I'll follow you in a couple of moments. But by the way, I don't know whether it was clear from what Adam explained. What he was talking about was processing these Ethernet packets. The Ethernet packets have got stock trade information. They contain stock trade information. And what they want to do is they want to process that stock trade information and know when to buy or sell some stock holding. Need not be in a particular stock, might be with something completely different. So the normal way that this would be done is you have Ethernet packets coming into the network card, and then that network card, those packets, the information in them has to be transferred to the host by PCIe, where they get processed and back again before some result is known. And that's a fairly slow process because PCIe is quite slow, and the processor at best is multi-threaded, so it's not really going to be operating particularly quickly. Much better is if you can process those packets on the network interface itself, and that's where FPGA is induced inside these network cards to do a lot of the packet processing to determine whether or not particular trade should occur based on an observation of the trades that are occurring in the market. I hope that's clear. Any questions? Right. I don't even have to look at the board. I know exactly that means that it's also the product of max term 0, 2, 3, 7, right? Because just the ones that are missing from the list. That corresponds to all the zeros that I see. 0, 2, 3, and 7. Right, but that's not the canonical sum of products, or the product of sums. That is this guy. It's 1, it's 2, it's 3, and it's 1, so, or it's 1, it's 2, it's 3. This guy is in theorem of these guys. So in the first case, the first and the third term, 1 and 5, that allows me to eliminate x1, right? So I'm left with x2 bar x3, and for the second and the fourth term, I can eliminate x2 because that appears in complemented and uncomplemented form. So I've got x1, x3 bar, right? How I simplify this any further? What if it has the guess? How to simplify this any further? So what's the cost of this expression? 2 inverters, 2 OR gates, and an AND gate, so that's 5 gates. Mm-hmm. 1, 2, 4, 6, 8. That's total cost of 13. Yep. So what happens if we play around with this a little bit? If we distribute across a x1, x2 bar, or x1, x3 bar, or x2 bar, x3, or x3 bar, x3, I don't have anything. So that's fine. You let go of that. So now I have x2 that's common to both these, so I can distribute over that again. So that would be x2 outside of x1 or x3. Right? And I've got x1 and x3. 3, 5. Anybody see anything there? Yeah, that one. The last. Yeah, it's the last one. Anybody remember what it was called? I think it's the consensus in studying C. Yeah, you're right. Why is this? It's kind of sense. It's because I have x3 appearing complemented and uncomplemented, added with x1 and not x2. That happens in either term I've got there. So I can eliminate that guy and just write it like that. And isn't that the same as what we've got over here? What's the cost of this expression? This expression here, I've got 2 inverters plus 2 AND gates plus an OR gate. So I've got 5 gates.
Yeah.
I've got 2 inputs for the inverters. I've got 4, 6, 8 inputs. So it's no more expensive than what I had previously up there, the same cost. Okay. Any questions on that? Yeah. Okay, I'm just imagining if I line the gates, right? Every time there's a bar, that's an inverter. So it's just got one inverter, one input, but X2 to this inverter. So we should be drawing in a circuit, right? So this circuit, how does it look? Well, we have 2 AND gates that are being ORed together, right? And the inputs to these gates are as follows. I have X1 and I have X3, the other input to that guy, and down here I have another inverter in X2, right? So I've got 1, 2, 3, 4, 5 gates, and I've got the inputs to the inverters are 1. The inputs to the AND gate, there's 2 each, right? Because there's 2 terms in each of those AND gates. That's 2 wires here and the 2 wires there. And then finally, it's an OR of 2 and two product terms, right? So there's 2 inputs to that, so 8 altogether. All good? Yeah.
If I X1 plus X,
How do I divide it?
what do you get? X1 and X3.
Second line, meaning there or this line? This line, okay. By combining the first 2 terms here, effectively, in longhand, what this is equivalent to, if you use the distributed law, you've got X1 or X3 and, how do I do that? It's the uniting theorem. So let me just go to the theorem first. That's why here. Let's find the next one. So it's 9D over here. Does that take equal take? So what we have to do is prove that theorem to take it. We have X plus Y and X or not Y, right? Is that correct? Yeah. Which is equal to X and X or X and Y bar or X and Y or Y and Y bar. But that's 0. This is X. So this is equal to X or X and Y bar or X, Y, right? And X or X and Y, we're just doing absorption on this, right? Which is one of the other rules that we had there, number 10. But in longhand, that's X and 1 or X and Y bar, and then you can show plus XY or XY. We can show that the left-hand 2 terms are then just X and 1 or Y bar or xy, which is equal to x, because 1 or y bar is 1, 4xy. And we could play the same game again on x or xy and deduce that that's x, right? So all we have here is that x1 or x3, this plays the role of x in this expression, right? And we have x2 x2 first, and we have x1 or x3, which is playing the role of x, or not x2. So you get it from there? Okay. So I'm eliminating x2 effectively. It's the uniting theorem, but thinking about it from product of sums form. Yes, sir.
I have up the QS1. So the first bracket, it was according to that row table, it was by inverse, like the zero one for
This one,
the first bracket.
this one.
Yeah, this one.
That's the 0th row. That's right. That's max term 0.
Max. At the second bracket, with its
It must be max term 2. Right? So the way you can tell which max term it is by looking at where the complements are. So there's no complements here, so it must be 0. The complement here is in the second bit position, so if you think of no complements, zeros and complements 1, and this is binary value 2, and this has binary value 0. And so that's max term 2. Is that your question?
Like that. Actually, the first bracket and the third bracket, they are conversely according to the table, because like for the first table brackets, it should be all 0, and the first one is not inverse, but yeah.
I don't understand. What do you mean by first bracket should be all 0?
Like the first bracket is for row 0, and the second bracket is for row 2, and they are proportional to the table, so you can find.
Yeah.
But in the first,
That's for row 3, the response for row 7.
yeah, 7. But in first bracket with x1 is 0, it shows that x1 is positive. But the second bracket with x1 is 1, the x1 is positive.
Yes. I'm not too sure what you're referring to, but I think what you mean is if I shouldn't have propped that off. I can write it back up again. I think what you're referring to is the fact that each max term introduces a 0 in our expression, right? Now I'm going to hurry up here because I do want to get a few slides into the next lecture. For max term 0, I have a 1 in row 0. Sorry, I have a 0 in row 0 and a 1 in every other row. 0, 1, 2, 3, 4, 5, 6, 7. For max term 2, I have a 0 in row 2 and a 1 in every other row. If I add these rows together, I get a 0, a 1, a 0, a 0, a 1, and so on. 1, 1, 0. Is that what you're asking about?
So the relation is x4.
No. No, they're being added together. Each one of these that's what the pi refers to. We're adding these max terms together. F is equal to the product of all of those max terms. Right? And it's the 0, where the 0 occurs in each of those max terms that then determines that there be a zero in the corresponding function. Whereas for the sum of min terms, each one of these contributes a 1 only in the row that corresponds to it, right? Here's the one from min term 1. Here's the one from min term 4. Here's the one from min term 5. And here's the one from min term 6. Okay? Right. Are there any other sort of questions that we haven't sort of already talked about in some way? Okay. In that case, let me skip just to the end of this set of slides. Just the next slide is a summary of where we've come from, where we're up to. Logic design concerned with finding the least cost implementation of combinational, there's sometimes also called combinatorial. I don't like that name quite so much. Logic functions. These are called combinational logic when we're combining different variables together. The circuit cost is measured by summing the number of gates and the total number of gate inputs. We've talked about the axioms and theorems of Boolean algebra and using those to minimize the cost of the combinational logic function. We usually apply them one at a time with the objective of eliminating one or more variables from the term for whole terms from the function, as we've seen on a number of occasions now. There are two canonical representations of combinational logic functions, the canonical sum of products and the canonical product of sums. Canonical sum of products represents a function as a sum of min terms, and the canonical product of sums represents a function as a product of max terms. Okay? So that's all we really know so far. All right. I know you're struggling. It's Friday of week 1. It's time to go to the bar or wherever. It's time to relax. But I'm going to demand your attention for another 10 to 15 minutes, if I may, just to get you going with the next bit, because there's one thing that you will have seen in the labs that we haven't talked about in the lecture that I think is, well, maybe there's quite a few things, but there's one obvious one that I want to at least cover off a little bit. And that brings us to this second lecture, where if you think you've seen it all about how to simplify functions, you have it by a long shot. Believe me, we've been designing circuits for a long time, and prior to that, there was more theory behind it all. So we'll be learning more about the synthesis and analysis of logic functions. How do you use a graphical form of Carnot math, which I'll introduce right now, for drawing, for graphically deriving a simpler implementation of the function. And I want to talk a little bit more about FPGAs to implement logic functions and the use of CAD tools and the FDL to implement logic functions. And eventually we'll get to talking NAND and NOR gates as well to implement logic functions. Because the interesting thing about those gates is we only need the one type of gate. We don't have to worry about 3 types and or not. You just use a NAND or NOR logic as your universal gate. Right. Going to start off with a familiar theme, another truth table. I don't think we've seen this function before. So it'll be in terms 0, 2, 4, 5, and 6, right? What's the product of max terms for this function? 1, 3. Yes, I think I've heard enough correct answers there, 1, 3, and 7. Okay, so we've got this sum of min terms. Obviously, that can be elaborated. And what we've been doing is using uniting theorem primarily to simplify that expression. sometimes it's a little unclear. It's not too bad in this one to see that we can't simplify that any further. There's not enough terms to apply the consensus theorem. There's no way we can combine these to say 3 different variables using the other theorems that we've seen. All right. Now, we also started talking about how to implement or specify these circuits to be actually in the FPL. And what we saw in the first lecture was the use of the data type bit, and we saw the use of a concurrent signal, simple signal assignment statement like this to define what the output of the function should be. Now, unfortunately, type bit only has 2 data values, 0 and 1. And early on, when VHDL was really only used for modeling systems, that was adequate modeling at a high level. But as more and more uses were made, it became obvious that we needed more data types than just type bit. So the IEEE introduced the standard format card 1164 to introduce a new data type standard logic that provides 9 different values for data. So apart from, 0 and 1, it's possible that an electrical signal in reality will have a few other values. It might be unknown, for example, or it might be uninitialized, which are sort of the U and the X that we see in this list of values. Sometimes we don't really care what the value of a signal is, so that we give the CAD tool freedom to choose an optimization that is best. And there's, in order to understand how systems that are not correctly wired up together are behaving, also we use weak signals that are either 0 or 1 as well. Anyway, this standard logic package defines how signals of type standard logic are combined together using AND, or, and NOT. And so if we want to make use of this more general data type, we have to include these 2 lines before every design entity in the HDL. So every time you want to describe some circuit, you need to include these 2 lines at the beginning. Include the IEEE library and make use of the IEEE standard logic 1164 package, namely all of it, not just some subset of it. They're the 2 main changes that you need to make. Then you can refer to data items of type standard logic. A long story short, we don't really need to worry too much about that. Just do this so that you can make use of those signals. However you express this function in VHDL, the CAD tool should synthesize it down to this. It should be clever enough to figure out what's the optimal way of implementing that function. So it doesn't matter whether you explain or describe the function using a canonical form or some semi-simplified form. In the end, the CAD tool should be able to simplify it. Check that it's got the most simple implementation. There are sophisticated CAD tools and theory that underlie how a CAD tool does that. We're going to go in the direction that explains how the CAD tool does that, but we're not going to show you the final form. That is explained in the text if you wish to learn about it, but it's a bit esoteric and not really necessary to understand how to implement circuits in hardware. That's really an advanced topic. So the Carnot map is a way of systematically figuring out whether or not you've simplified the Boolean expression that you have. as much as you can. So remember that we make use of the uniting theorem, either in its sum product or product of some form, ultimately to simplify our expressions. Carnot map lays out the min terms or max terms in a two-dimensional array so that those terms that you can combine are next to each other. And so you can see whether you have either two ones or two zeros in the map that are adjacent and therefore can be combined using the uniting theorem. So without further ado, I'll show you a few examples. This is not going to be terribly deep and meaningful. We'll get into definitions next Tuesday so that you'll be able to do this as well. So given a two-variable truth table, as we have over here, with min terms 0 through 3, then notice min terms in a two-dimensional, two-variable Carnot map are laid out in a certain way. We draw a 4-entry table like this, and we lay out the first two min terms in the first column and the last two min terms in the second column. The reason we lay them out that way is that it depends on how the table is labeled. In this particular case, we've labeled columns of the table using the variable x1. In the left column, x1 has value 0, and in the right column, x1 has value 1. The rows of the table are labeled by the variable x2. That's the less significant variable in this table, given that we've enumerated the table this way. In the top row, x2 has value 0, and in the bottom row, x2 has a value 1. And so you see that min terms, them in 0, 0, 0, 1, 1, 0, 1, 1, they're the binary values for the min terms, if you like, are laid out in such a way that those that are either horizontally or vertically adjacent differ in only one bit. And therefore, we can use the uniting theorem to eliminate corresponding variable. Okay? Here we see that min term 0, which has valuation 0, 0, is above min term 1, which has valuation 0, 1. So if both of those could be combined in some way, we would be eliminating the less significant variable, namely x2, right? And that would correspond to the situation where x1 is 0. Similarly, if we look horizontally across either the top or the bottom row, we see that those min terms differ in the first gate position. Namely, in the first row here, we see that x1 is 0 in the first column, and x1 is 1 in the right column, whereas x2 is 0 in both of those cells. And so by combining the two, we would eliminate x1 and be left with x2 0 or x2 bar. So let's have a look at how that looks when we map a real function into the map. Here we see the function 1, 1, 0, 0, 0, 1, corresponding to min terms 0, 1, and 3, being laid out in Carnot map. So we have the 1 from the topmost row, or row 0, 0, the 1 from the second row, or 0, 1, the 0 from the third row, 1, 0, and the 1 from the fourth row, 1, 1. Now we could combine those neighboring ones together in order to simplify the function. So two ones that are on top of each other, they correspond to the min terms, not x1, not x2, and not x1, x2. And so not x1 is common to both, x2 could be eliminated using the uniting theorem. And so that corresponds to the fact that in this column, x1 is 0, or x1 is inverted. But we've covered both possibilities of x2 being complemented or not complemented. And so we can eliminate that second literal variable from our chain there. Similarly, the two ones down at the bottom could be combined because they're next to each other. They represent two min terms, not x1, x2, and x1, x2. So x1 be eliminated. That row then corresponds to the row x2 is 1 or x2 being of the map. Okay, so we can use the fact that neighboring cells could be combined to systematically eliminate those variables. We don't have to use the Boolean algebra or in algebra. A 3-variable map looks like this. We can't draw a square 8-entry tape, so we have to make a decision that we're going to have more significant variables, so more columns, or we're going to have more rows in our table. By default, we always prefer in this course having more columns in our table than rows, where it's an uneven number. In this case, we map the first 2 mean terms into the leftmost column. The next 2 mean terms go into the second but left column. The second last 2 rows, they actually get mapped over into the right-hand column of the table, and the last 2 inputs get mapped into this second but rightmost column. So it's a bit of an unusual ordering. And that comes about by the way that we designate the column valuations for x1 and x2. We have 0, 0 in the left column, 0, 1 next to it, corresponding to x1 being 0 and x2 being 1. But if we this column, this valuation of x1 being 1 and x2 being 0 next to this valuation, we'd have 2 bits splitting. Therefore, we would break that requirement that we're only changing 1 bit, or we're only different neighboring cells only differing 1 bit. So we prefer to have 1, 1 next to 0, 1 and 1, 0 in the middle of it. This is called the so-called gray numbering or gray encoding of the columns. Right. So it's a slightly unusual ordering. Of course, the first row, all of the entries have x3 to 0. That's the least significant bit is always 0. And the bottom row has every entry having x3 equal to 1, corresponding to x3 being 1. All right. So let's have a look at a real implementation here. Here's a function, and that gets mapped. The first column, the second column. Remember that the third column here has to be mapped over to the right-hand side of the map. Then finally, we have the fourth column. Actually, just going to go back and make one more observation. You should also be able to see that the left and right sides of this table are adjacent as well, or should be considered to be adjacent, because they differ in only 1 bit, right? In each case, it's the rightmost column has x1 equal to 1, and the leftmost column has x1 equal to 0. So they only differ in that x1 bit. So you can think of this table as being curved around, forming a cylinder. It's also clear that this bottom row is adjacent to the top row, and so the bottom edge is actually the adjacent top edge of the table, and that becomes more important with larger Carnot maps. In effect, we have adjacency on all the edges in this table. The left edge is adjacent to the right edge, and the top edge is adjacent to the bottom edge. So effectively, this map is a 2D, a flattened torus. We have a donut there. We join the left and right edges, we've got a cylinder, and if we join the top and the bottom, we get a donut out of that, right? Okay, so we've mapped our function here. What does that simplify? Well, how does that simplify? Well, that's given here. These 2 ones are adjacent, so we can combine them and eliminate x2 there, as you should be able to see. Therefore, the resulting term is just x1 and x3 is complemented in this row. For the other 2 ones, well, they're adjacent because of this torus nature of the map. So the left column and the right column differ in x1. So x1 will eliminate, we have not x2 and x3 because we're in the bottom row. Okay. I guess some, when you're starting, might think, well, we have to sort of worried about these two ones here. They're next to each other as well. You can see that here in the right column of the table. We don't need to worry about those. We've already covered all the ones in our map. Okay. So more on that theory next Tuesday. Here's another function. Over here, we see the first two entries going to the left column, the next two entries, the next column, the last two entries, 1, 1 coming at the back end here, and then finally the 1, 0 going into these two entries of the map. Now we see all of the row x3 to 0 being covered with adjacent ones. So that corresponds to the term not x3. By covering all one, we're eliminating two variables to be left with not x3. But what about this term at the back there? What's that? That has x3 equal to 0 and x3 1, but constantly x1 equal 1 and not x2. So they're the two terms on the left. When we simplify that function, no Boolean algebra needed, right? This is what a four-variable map looks like. In this particular case, then we have gradient coding over the columns and the rows, and I can't really keep it in long to sort of all these to three. Stop. Sorry about that. Any questions? Maybe wait till after the class I felt packed up. Seems like there's another class that may be able to come in. That's really. What? Good. F. Dolly. Back. Not yet. Come on out, fellow. I see you. Get the issue. You didn't get both. The friends that you really my archie when you're great, don't to that. Yeah. Now the US attack. Yo. Yep. All good. And you get them. Why do you do it to me? But yet, can you just wait until I've packed up and I'll come out here if you show me? So it's question, I remember that you said, and it's all your in what you call the this doing this. This is an exercise. So noted must be following. They are on their way to that. What when you're talking about each, you need the next has to be in growth. Mean for that, by mean term. So that's the mean term. 0 is 1 in that row, and it's 0 in all other rows. Yeah. So what does the mean term? And that's in the God do there. And understanding the question, people try to phrase the question like, well, what's this? It just needs to not the variables that has this value in these rows. Right? What I asked you to do was to try and provide a sum of products and a product of sums expression for that function. So using the internet, there will be some products using max term, the product of some spreadsheet data. So to derive a sum of products, you have to find all the ones that they can use. So you have a one for intern 1, you have a one for intern 5, 6, and 7. 4, 5, and 6. So suddenly the intern is 1, 4, 5, 6.